Hi, welcome to this ZP Developer Zone webinar. So we like to do this every Thursday at 8 a.m. London time. We have actually come on about 52 minutes early. I apologize for that. There's just a lot of meetings, etc. today. And it's recorded, so you can sort of find this anyway online. Let me jump straight into it and just say that we obviously have the ZP Academy. If you're looking for free educational material, there's a couple of free courses there. And there's the webinar. We do this every approximately Thursday, on Thursdays about 8 a.m. London time. We have our collaborations. He's definitely running the universities we've hired in Norway. We have our ZP Developer Zone, and we have our workshops. Our workshops are probably the thing that's best at closing the gap between people's kind of wants and their current understandings. So we do have a workshop. We actually have one next week in Coventry in the UK. So if you're in the UK next week, please let us know, because we do have a workshop running in Coventry on exactly next week. We have them in September, both in the UK and in Norway. And we also have one on neurosciences, biosensors for neurosciences. We also have a large Scandinavia conference as well. So we do have this large conference running on the 13th and 14th of September. Any links, I will put them underneath the video, and it's probably worth saying that will be some very important links in a bit. So the question this week that have come in are how do we detect or how do we make sensors for arterial blood gas analyzers? I will discuss that. A quick question on the measurement of pH on an Arduino. I did answer it during the week, and I think the person's probably already taken action upon it, but I'll just mention it anyway. How to make a chloride resilient electrode. In the first instance, I don't ask people to make chloride resilient electrodes, especially if they're doing things like arterial blood gas analyzers. You don't necessarily need it. And getting into chloride resilient electrodes is kind of adding an extra layer of complexity. It's best to really crawl before you start running, I would say. I'll also talk about wearable biosensors just briefly. I happen to have a wearable biosensor here today, so I will discuss that. I'll probably also discuss the fact that I have a few of these on me as well. I'll just hold one up now. These electrodes are very indicative of the types of electrodes that are used in arterial blood gas analyzers. Anyway, that said, I will go forward. I will talk about the detection of pathogens, at least the R&D side of things. I will talk about electrode arrays. We've got this array on our website, which is kind of 9 working electrodes, a common counter and common reference. I'm not sure that we have an off-the-shelf electronics for it. We built it for ourselves. We use it on projects, but I don't think we have an off-the-shelf electronics for it. And I'll finally finish with just a very quick comment on the measurement of melatonin. So first things is with arterial blood gas analyzers. This is a blood gas analyzer from a company called Radiometer. Radiometer, I'm very kind of familiar with their technology. And by the way, I do cover this in our workshops as well. They use a very similar technology to this, which we have at ZP. So I'm sort of familiar with what they're doing. I'm very familiar with what we're doing. So what we do is, I'd say we're on similar technology platforms, certainly manufacturing platforms. So the technology that we have at ZP is really applicable to arterial blood gas analyzers. People always have lots of questions, and this is a classic question, is what is your accuracy? And it's really important because people come to us and say, I'm interested in your sensor, your electrodes. Okay, so that's that. That is such a small component of the total system. So the accuracy that you can get from our sensors comes from the accuracy of the entire system. And I'll talk about some of those kind of calibration routines, wash routines, how you bring the sample in a repeatable manner to the sensor. These are important. What are your electronics? These are important matters. How do you extract the signal from the information from the raw signal? So accuracy is not a ZP question. Accuracy is actually a system level question, and I think our quality team would work with you on that definition of accuracy, because that's a system level. That's really what your product will have, not whether our underlying sensors have it. The underlying accuracy that we get comes from from the total system. So I do get that question a lot. Are they best suited for? Can we test whole blood? I think was one of the questions. Are we suited for ABGs? We are. If you come to one of our workshops, I will lay out. This is some of the on the market technologies. You'll understand the similarities. We would develop software specifically for it, but it's probably worth saying that we are ISO 13485. We can develop software, and we do develop software, and we do it within a sort of ISO 13485 framework. This is not the same as just normal software development, which can be a bit more loose. It has to be a bit more controlled when making medical devices. And also it says here, well, why do you limit your sensors to 6 months? Now, 6 months is a good indication, but whether you can get 6, 12, or 18 months is really a system level output. It's not linked to our sensor alone. It's linked to your entire system, and you have to engage with ZP as a kind of contract consultant to actually really advise on this kind of material. We obviously do have an off-the-shelf pH. We have lots of the electrolytes. We have these PO2s, or these oxygen ones, dissolved oxygen. We have the glucose. Anything I listed here, we definitely have it on the shelf at ZP. And I also wrote an article about ZP's use of ZP sensors in blood gas analyzers. So I don't want to waste your time by repeating things that I've put in the public domain in the past. After this webinar, I will go on and edit and make sure I try and get all the links underneath the video. So on that page, I do have a discussion about, the question about accuracy and about like length of time that sensors can be used for really comes down to some of these points, which is, what is the calibration routine that you're going to implement? If you don't know, contract with ZP. What's going to be your sensor wash routine so that you can sort of test lots of different samples on the same sensor? If you're not sure, come and consult with ZP. What are going to be your electronics? Electronics will have, I have a few slides on that, so I do have recommendation on electronics, but if you're not sure how to implement them, please come and talk to CB. Methods of analysis. This is whether you use amperometry or potentiometry. Open circuit potential, I would say, is really a sort of form of potentiometry, but it's an important measurement technique. Voltammetry is also an important technique. What methods of analysis are you going to use? What signal processing will you use? Because signal processing will improve accuracy. I have a video in this in this slide deck today that shows you how we can actually, it's not accuracy we play with, it's limit of detection. But you can change the limit of detection quite dramatically by how you analyze your signal. It's the same for these sensors as well. So the question is not what is ZP sensors accuracies. The question is work with ZP, contract them in, start putting their sensors into your technology, and let us guide you on how you would use the sensors in your system, because accuracy is a system level thing. It's not a individual sensor level thing. And then obviously, how all this gets integrated and works together is everything. That these sensors alone, the accuracy and performance of these sensors alone is a function of how you use a sensor in the system. But fundamentally, these kind of electrodes and sensors are used in blood gas analyzers. Pull apart some on the market, you'll find them there. But I would say contract with ZP to advise on this. Side note on electronics, we do have a very nice small set of electronics. This is then being used in a glucose sensor, and I've put some links to the data sheets, etc. here. So if you've got engineers, they can pore over that, but realistically, we do have a bit of a sort of try and buy policy, so I should say buy and try policy. Buy it, try it, if you're not wanting to engage with our contract services. There will be techniques that you will have to use and become familiar with. If you're not familiar with them, then I would definitely suggest coming on one of the workshops. But amperometry, you're going to have to become super familiar with it. Voltammetry, potentiometry, and impedance. In fact, I can think that all of these techniques will be used on a blood gas analyzer. Amperometry for glucose, voltammetry for something like hematocrit, potentiometry for the ion selective electrodes, impedance for doing a hematocrit as well, and also calculating things like hemoglobin. Extraction of signal. This is one of those bullet points I listed earlier on. I have a video on this where I say, look, this is the same data, and whether I analyze it in different time segments, I can really affect the limit of detection. So this is a software system called Julie. It's a cloud system. Anyone who's working with Zimmer and Peacock, they can either just buy a license to it anyway and just use it themselves, or anyone who's working with ZP gets to also use this system as well, and we can use it to rapidly analyze data. And in this video, which I have got a link to here, I demonstrate how actually we can really play with the limit of detection by just from the same signal. So, and I use that as a good example of accuracy. Accuracy is definitely the way that your system interacts with the sensor. We do have a webinar next week on the 8th of August. So if you're so inclined, it's a free webinar on Julie. So I put a link here, and I will make sure I edit this video online afterwards to put the links underneath the video as well. We also have a technical webinar as well next week. It's primarily intended for people in India, but you can sign up to that on the 9th of August as well. And I've put a link to it here. Software-wise, one of the questions was, can we be involved in this? Well, a blood gas analyzer. See, the system that your product is not yet built. It's not, and I suspect it's in some degree it's still a sort of at the idea stage. But at ZP, we do develop a lot of software, and the software for a blood gas analyzer will be a very will be a different piece of software. But at ZP, we do develop software all the time in order to run ZP sensors and also client sensors as well. So it is a skill that we have under our ISO 13485. People do ask whether we outsource it. We don't, because our software often works with hardware, and so it's not just a pure software play. So they were particularly interested in particular sensors. I have highlighted the ones that are on the website. So we have the pH, we have the oxygen, the sodium, the potassium, the chloride, the calcium, the glucose, the lactate. If you're not looking to engage ZP, then I would just say buy the potassium and play with it, buy the glucose and play with it. That will sort of give you a good, let's say, start on your journey. Question number 2, measuring pH on Arduino. I do have a link to this video as well. But these people, now at ZP, we do not support the use of our sensors with Arduino, but we do what I would call sort of good work and good community work. So we do make little videos to help people out on occasions, but then we will not then afterwards support the video, especially this one. I think it's like 2018 or something like that we made this video, so it's been some time. But in the video, the person asked, and they've been following this video, and they're polite people, so we said, okay, I'll take a quick look at it. And so their question was, they knew the working electrodes connected to the central pin on the BNC, but did the counter and reference get shorted to the external shield? And the quick answer is yes. We rewatched the video, and I think at about 26 seconds, Andre does say yes, he did. So we don't support this. We've had a quick glance at it, and we think the answer to your question is yes. I've linked to that YouTube video here as well. I hopefully have put that link underneath the video as well. As I say, people can do this kind of work, but ZP is a commercial organization. We do have our own solutions for this, which we support. And if we do choose to kind of give you some advice on our webinar, etc., I mean, it's just out of goodwill. It's not, if you say, oh, it didn't work, sorry, okay? That's between you and Arduino. Question number 3, I do tell people, don't go for a chloride resilient reference electrode when you first start. I do say, look, go for it without this chloride resilient electrode, but later on we can add that kind of complexity. in this particular question, they were asking, you know, well, how do I use the solution? They do actually have the solution, and so we haven't optimized this, by the way. This is just the free advice that we kind of give out. But I realized looking at this that this does need optimization, because it says here, decant 300 microliters of the chloride resilient premix, okay, and then add in 10 microliters of the activation solution. So you've now kind of got 310 microliters. And then it says add 3 microliters of the solution to, you know, let's say to the target, and wait 24 hours. That means you just wasted about 307 microliters. That's extremely wasteful. So you really have to think about how much volumes you're actually going to mix. So you don't want to be wasting this. And then we say add a further 300 microliters, but it should really say add a further 3 microliters 24 hours later. But it should be a fresh solution each time. So you really have to optimize on this, you know, that you have to make a solution on day one. It has to be quite small volume. You probably have to do it in the ratio that we suggested, and you put it on your sensors. But the next day you have to make a fresh solution, put it on your sensors. The next day you have to make a fresh solution and put it on your sensors. This is not optimized. I would call this, use this as guidance, but this is not optimized. But I do have a link to the to it here, if I can say that. Question number 4 was, can you make wearable sensors that detect vitamins and mineral levels in the body? A quick answer is we can. This is one of the technologies that we own at Zimmer & Peacock. A lot of our technology stack at this point has had millions put into it. I mean, this technology is a wearable microneedle technology. It's not something you'll find a lot on our website. This has had at least 3 million invested in it, and it's a wearable biosensor. So it has microneedles there that push through my skin, and the rest of this electronics is really just the electronics to drive that microneedle array. So at Zimmer & Peacock, we do have some very sophisticated electronics, biosensors, wearable biosensors. Can we measure vitamins and minerals in the body? Yes, we can. I don't put this on the web store because this kind of technology is so advanced, if I can say, and really quite expensive that, you know, people have to engage really correctly with a company like ZP in order to access this kind of technology. But this technology does exist. Obviously, it's Bluetooth enabled, etc., so we can get the data out there. So the quick answer is yes. It's not something that we make super available on the web store because it's so expensive to get to that stage. It's a real piece of work, I would say. Question number 5. Right, so we got lots of questions here. So somebody wants to measure something like a pathogen and the proliferation of a pathogen, and using impedance spectroscopy is not a bad way of doing it. The first thing you have to do is not think about the in vivo experiments or the in vivo application. You have to get the in vitro experiments done. That's your lab experiments. I said it a few times in different contexts today, but you really got to walk before you can run on this. But I have recommended to them, they've asked for a gold electrode. I can't keep recommending it. There is a gold electrode. It's pretty good. And what's nice is that we do use that gold electrode in impedance experiments. Now, in this impedance experiment, we're looking at the effect of material on the surface of the electrode. This person's signal will be between the electrodes, what I would call the solution resistance. But really, they just need to do the experiments or start doing the experiments on these gold electrodes and looking at how the solution resistance changes as a function of time. And as long as the cells are proliferating, I think they're going to get quite a strong signal. This is 3 sensors at one sort of level of loading. This is another 3 sensors at another level of loading. This is another 3 sensors at another level of loading. And this is another 3 sensors at another level of loading. I would describe that as my calibration experiment. ZP is quite unusual that if we are involved in the development cycle, then because we're using our electrodes, and as long as we are involved, the repeatability of our electrodes and therefore the experiments on top means that you can come up with calibration routines that are then translatable to the field. People have a real problem with screen printed electrodes. It's because they're not reproducible. Therefore, they have to actually do calibration in the real world, which is really, you can't do it. It's not a good idea to do it. You can do it in things like the blood gas analysis that I was talking about earlier on. That's fine because that instrument it has size, it has volume, you can have calibration solutions on it. That's a good place to be doing calibration and wash. But when you're trying to do, this is a wearable biosensor, an application like this, where it be wearable and implantable, you cannot do calibration in the field. You can do things like relative change in signal over time and call that your signal. I think that's a better way of doing it. But that said, in this particular application, the person basically needs to get on with experiments and actually just look at first of all, what their signal looks like. And then they can start worrying about the calibration and how to convert that signal into, can I call it cell density or pathogen count or CFU, colony forming units. That's the kind of work we're really good at ZP, especially that idea of colony forming units. They're also interested in how to clean the electrodes. So there is a video on this. And though we didn't say the volumes exactly, I mean, I did watch the video and I could see the scientist doing the cleaning in that particular video. I mean, I'm enough of a sort of scientist to say that I think what she's putting on here is about 50 microliters. So she kind of cleans it with about 50 microliters. She just leaves it on there for a few seconds. So this is really the sort of optimization that people need to do as well. But, I'd leave that on there for 30 seconds. I don't want to sort of say what she says in the video, but I suppose I was just watching along and it was, it was approximately 30 seconds. She then gets out a bit of a rinse solution. And she just starts sort of rinsing it off a few times. So it's not super rocket science as to what we're doing. And I would honestly just follow the video. Sort of 50 microliters is fine for the cleaning and the wash steps. And you can see she does quite a few wash steps there as well. So seriously, just follow along with the video and you should be fine. The person's asking here, should I be measuring conductivity or capacitance? I think the fact is that question comes when you've got your data. We gather the data and then we say, okay, now we've got our data, especially if people are working with us, we can put the data into Julie and very quickly optimize what is the best way of extracting the information out of the data. But at this stage, don't ask the question whether it's better to use conductivity or capacitance, because both sources of signal, both parts of that signal are in the raw data. So you don't need to ask the question, you need to get the experiments done, because then you can extract, or you can determine that for yourself. By the way, we do use both, depending on which gives us the strongest signal. I have recommended here, these are the electrodes, these are the connectors, this is the instrument, this is the cable. You're ready to go. It's important people start, because I think sometimes it's the sort of, all the questions is like, get in the lab, fail fast, learn quickly, iterate. You've got to get going. Question number 6. This is the hardest question really, because they did ask us for a sketch. The reason I don't put a sketch up there is I used to have a sketch up there and somebody just sketched it and just made it themselves, which is fine, it's no big issue. But I say if you want a sketch of it, buy some, because then you can essentially, you can copy it that way. But if I put a sketch up on the internet, it just gets copied. What would the full assembly of the electrode look like? This is not necessarily a single purpose biosensor, by the way. This is an array of electrodes that we would typically put a sample onto the tip of this. So just a quick glance at that, something like 50 microliters to 75 microliters will probably be enough to cover that. So we would use that as a sort of 9 working electrodes analyzing a sample in the range 50 to 75 microliters. Now he's asking, I'll describe, we don't really have we don't have a 9-channel potentiostat to do that. I have a 6-channel, but we don't have a 9-channel potentiostat to do this. You could, for example, have if you were really smart, we do have these kind of solutions. You could functionalize one of these to be glucose, and you could functionalize one of these to be lactate, and you could measure those 2 analytes in the same sample. How you do it is you basically need a multi-channel potentiostat where you can apply different potentials to different electrodes. If you're not sure, that really is a workshop question, because it's quite, I mean, it's hard enough to describe how to do one analyte at a time, but here I'm trying to describe how to do 9 analytes at a time. But it's something that typically we would make biosensors doing 6 analytes at a time. We do have quite a lot of technology around that, but in theory you can do sodium, potassium, chloride, glucose, etc. on something like this. I'm not going to today talk about manufacturing yields, and if people did ask me questions about that, I think we would charge that as a consulting thing, but there can be quite an impact the more complex your device, the more analytes on it, the lower your yield. I mean, that's the sort of hint, if I could put it that way. It is okay to just have these 9 electrodes and a common reference and a common counter. It really is quite common to do that, and to be able to have different potentials at different electrodes. We do have a connector for this, so and I've put the links to these, the array and the connector here, and we do also have a bit of data where we sort of we use this to measure pH. So it was all the same target, and we measure pH, and I did put a link to that. But this is a product that we've made, and we make it available on the web store, but it's not something that I'm able to necessarily answer and give this person an off-the-shelf solution for all of their questions and problems. The closest that we have to a potentiostat that is able to measure that device is this. This is 6 channels. It's called EMMA. If they went ahead and purchased it, we could probably come up with a cable for them then, so that they could connect between the 2 devices. But I think at the moment they're just in their exploratory phase. Question number 7 was, can we measure melatonin? I did answer this question. I'll just be very quick about it. The quick answer is we can measure melatonin. They were asking whether we can measure melatonin in the plasma phase or in the liquid phase. Definitely cannot measure melatonin in the plasma phase. They may mean gas phase or vapor phase, but those kind of phases are really hard. At ZP we have measured in the vapor phase. But the quick answer is I'd rather much take the second one, which is, can I measure in the liquid phase? The quick answer is yes, and we can measure melatonin in the liquid phase. And we do have a platform called SenseIt-All. So if somebody wants to measure a single analyte and they want to come up with a minimally viable product really quickly, then we do have an excellent platform for that. We do have some workshops in September. As I say, we do actually have a workshop next week as well, and we do have a few slots that have become available on that as well. So questions, number 1, arterial blood gas analyzers, the technology that's on our website and the links that I have sent you. I am extremely familiar with industrial electrochemistry and its use of sensors in blood gas analyzers, and the quick answer is there's a commercial product you can take a look at, and the technologies are similar what I'm explaining to you in this webinar to those. Measuring pH on an Arduino, sure, we don't really support the Arduino. We do things like that because I think as a company we want to do good, but we can't forever support videos from 2018. But we did a quick look at it, and I think at the 26 seconds into that video it does answer your question. Wearable biosensors, yes, we can do wearable biosensors for vitamins, nutrients, but that technology stack has at least had 3 million spent on it so far. Pathogens, I've identified the gold electrode, I've identified the connector, I've identified the Anapod EIS, I've identified the cable. Literally, it's time to start putting samples onto that system and looking at the data first of all. Electrode array, I didn't have a great answer on this. We don't put drawings on the website, but you can purchase it and take a good look at it that way. We have the EMMA. The EMMA will only measure 6 of those electrodes, so you may end up having to build your own electronics to drive that. We have built our own electronics in the past. I put a bit of a page up on it, and I put a link, but it's not something we're supporting. It's just something we did in the past. And then the final one is a much easier question in life is, can you measure this? And the answer is yes, if we can. And this question was, can you measure melatonin? Yes, we can. It was just melatonin. That's so much simpler than many of the other questions today. And so we do have an entire platform for that. So I want to say thank you very much. I appreciate that. I'm sure it felt very long for you, but there was a lot to get through. I'm sorry I had to do it forward earlier than I was otherwise said. We just got a lot going on today. Okay, thanks very much.